Yes, class. So last chapter we are left with, that is semiconductors. So in the starting portion of semiconductors, we have classification of solids. See, three types of solids are there, basic three types. Conductors are present where metals and all are included, and then insulators are there, which are poor in conductivity. In between the materials which have the properties, in between the properties of conductor and insulators. These are known as semiconductors. So basic differences are there that we have to identify. Firstly, is basis on the basis of physical properties and certain conductivities and resistivities. Like conductors have low values of resistivity. Insulators have resistivity. So semiconductors will have resistivity in between these two. When you talk about conductivity, the conductivity will be high for conductor and low conductivity will be for insulators. So again, semiconductors will be having intermediate conductivities or resistivities between the values of conductors and resistors. And why do we have so much applications of semiconductors? Though conductors and insulators have different properties, so why semiconductors have excessive use, industrial use, and rest of the applications is because it's the ability to control current. How can we control current? That is not a part of your syllabus. Many portions of semiconductors have been deleted from your syllabus. Even from last year, some portions were added that have been deleted this year as well. Like special purposes diodes are not part of your syllabus. Transistors and all, do not do it. Logic gates, you don't have to study. Just few topics are there, revise those well and try to get a good score. Note down this page, then I'll discuss some more things with you. See, next type of classification is on the basis of band theory, which we see. So two types of bands are there, conduction band and valence band. Now, how do we differentiate all these three substances, insulators, conductors, semiconductors, based upon this band theory? That we'll see later on. First, just understand the meaning of what are all these bands. See, conduction band are those bands that have the free electrons in it. These electrons are available for conduction and to contribute to the electric current. Whereas this valence band that is present, or this valence band that you can see here in blue, this valence band, this valence band that is present. So this valence band has electrons, but these are bounded electrons. When sufficient energy is met, then this valence bonded electrons land up to the conduction band, and from there they are available for conduction. So these are different energy levels. All the electrons are associated onto different energy levels. So the above most layer of this becomes the highest energy level of valence band, while this layer becomes the lowest energy level of the conduction band. The gap that you see, the difference between the conduction band and valence band, that is known as energy band gap. So for different elements, this value is different. Like silicon, you will be seeing some value. For germanium, you will be seeing some values. So these are known as conduction band, valence band, and energy band. And differences based upon this theory, these are known as band gap theory. Band gap theory, we basically say. Now, see how to differentiate all the elements. See, for insulators, no, you will, for conductors, you will see that conduction band is partly filled with electrons. Valence band is completely filled and energy gap is present. Either you will see this first case like this. See, you can see here this is partly filled, or you will be able to see they are overlapping with each other. Either the gap will be present or this overlapping will be present. But how to identify whether it is for conductor? By just looking at the partly filled conduction band. In rest of the two, semiconductors and insulators, the conduction band will be completely empty. So if you see conduction band is partly filled, just identify it as insulators. So conduction band is partly filled, valence band is fully filled. Then you have insulators. In insulators, conduction band is empty, valence band is filled. But see, the energy gap is very large. Energy gap is more than 3 electron volts. If you are able to observe energy gap more than 3 electron volts, like this case, classifies it into it as an insulator. The way, for example, I have written here also, 6 electron volt energy gap is mentioned for diamond. So by just looking at the energy gap, that 6 electron volt, you can easily write that this is more than 3 electron volts. So definitely it will be an insulator, right? And see how to differentiate between semiconductors. In semiconductors, same thing, conduction band will be empty, valence band will be filled, but difference will be that the energy gap is very low. The band gap that we get now between conduction band and valence band, that is very less than 3 electron. So like silicon, I told you to remember it. Silicon and germanium, please remember these two values. These two values can be asked to you in the exams as well. So for silicon, it is 1.1 electron volt, and for germanium, it is 0.72 electron volt. So these two values can be asked to you easily, these two values for silicon and germanium. Right, so how to differentiate on the basis of band gap? Conductors, partly filled electrons in conduction band can overlap each other as well. For insulators, they won't overlap. Energy gap will be there, but energy gap will be large, more than 3 electron volts, and conduction band will be empty. In semiconductors also, conduction band will be empty, valence band will be fully filled, but energy gap is less than 3 electron volts. So by just looking at the energy gap, you should at least differentiate between semiconductors and insulators. And for conductors, just by looking the number of partly filled bands. So note down this part of energy band gap theory. Any doubts you have in between, get it cleared. Now see the types of semiconductors that are available. These are categorized into two groups. One is known as intrinsic semiconductors, other is known as extrinsic semiconductors. Intrinsic semiconductors are basically pure semiconductors. Means if you have one specific crystal, let's say you have silicon crystal lattice, then it will be having all the silicon atoms entirely throughout it. But if you mix some other atom, let's say you have added aluminium, let's say you have added phosphorus, you have added boron, any other element, you have added it and then made it extrinsic. So that impure element is known as extrinsic. So intrinsic and extrinsic, these are two types of semiconductors. Now, depending upon what type of impurity is added, we have other two types also, P type and N type semiconductors. Before we begin with intrinsic semiconductors, just see the concept of electrons and holes in this. See, these two silicon atoms are connected together with the help of electrons. If this electron gets removed, it's not present here. So that deficiency of electron will create a hole, positive hole. So holes are treated like special entities in semiconductors, but do not get confused. These are just deficiency of electrons. So either you say deficiency of electrons is holes and the negatively charged particles are holes. But what you can do, you can study it separately as well. You can use it separately. You can use the term hole separately, not just vacancy of electron. And you will be noticing we'll be having properties of holes. We'll be using holes properly. So that's why I'm saying, but do not get confused. It is actually deficiency of hole. So firstly, let us do the intrinsic semiconductor C. Intrinsic semiconductors are pure. Means, see, the silicon atom. Can you see all atoms that are present in this lattice are silicon atoms only? There is not presence of any other element. No other element is present that will be used in here. Like you can see, entire crystal will be of silicon. So these are just the electron bonds I have shown. Means the electron could have been shown like this. One electron bonded to other electron like this. So that has only been shown. These are the two electrons. It's just that one is shown like this, other is shown like this. The rest of it is same. The same thing has been shown over here. Now here what happens when the temperature increases, the thermal energy also increases. So the bond, this bond between the electrons, this breaks up. This electron bond breaks up. So what happens? The free electrons become available and they provide the electricity, like this intrinsic semiconductors work. Simple. And when the electron will leave, what will develop? Let's say this particular electron has left. You can see in the figure, this electron has left the original space. So what? A positive hole is left. A hole is left, no positive entity, hole is left. So if I say 5 electrons leave, then obviously you will say 5 holes will be created. So number of electrons are actually equal to number of holes. Here you can see number of electrons are equal to number of holes. So pure semiconductors, electron conducts electricity, number of electrons are equal to number of holes, temperature increases, thermal energy increases, electrons break, and the covalent bond between the electron makes the electron free to and available for conduction to occur. See, there are certain limitations for these intrinsic semiconductors. These say it is, see, number of electrons and number of holes are very small. If you take the value, take the magnitude, it is 10 to the power 6 per millimeter cube. That means, as I've written here, you can read it. In 1 meter cube, 10 to the power 6 electrons are present, which we say 10 to the power 6 meter cube. So these are so small that we require more amount of electrons. No, better number of electrons, better is the conductivity. And energy gap is also large for these. So that's why there was a requirement of extrinsic semiconductors. Means it was noticed that the pure intrinsic semiconductors are not very helpful. So extrinsic semiconductors were created. So extrinsic, I'll discuss first. You just note down these to some point, these introductory points. Then I'll discuss extrinsic semiconductors because that is lengthy and more important. See, impure means when some purity has been added. That when we'll discuss extrinsic semiconductors, no, then it will become more clear. Firstly, let us just copy it down. Then I'll tell you extrinsic semiconductors. That is more important than this.
Ma'am, can you scroll up? Done, ma'am.
Now class extrinsic semiconductors. Now see, first note that you were asking, Donna was also asking about the impurities. See, certain atoms are added to the crystal, pure crystal, any atom. So if in the pure crystal atom, you have added atoms, some other atoms from not from the same element. Like in the silicon crystal, I have added boron. So now it is impure. Something that was original, it is now impure. So these atoms that are added, these atoms are known as dopants, and this process is known as doping. So impure semiconductors which have desired impurity atoms in the crystal are known as dopants. So these dopants are added in the pure crystal, making the crystal impure. And these impurities are fruitful to us. These are very beneficial for us. Now, depending on the type of dopants, no, we have the types of extrinsic semiconductors. Initially in your notes also you have mentioned N-type and P-type. These are those only. So pentavalent dopants you have and trivalent dopants you have. Pentavalents are if these atoms, these have 5 electrons in their valence shell. The entire family of phosphorus, no, phosphorus, arsenic and all. These families have 5 electrons. How do you write it? Phosphorus to the power 5. And these are known as pentavalent dopants. And if these dopants have 3 electrons, like the entire boron family, boron, indium, aluminium, thallium, gallium, all these, they have 3 electrons in their valence shell. So these are known as trivalent dopants. All right, so now how I have classified extrinsic is based on this only. See, if pentavalent dopants are added, we say it N-type of semiconductors, and if trivalent dopants are added, we say it is P-type semiconductors. But see, when I had added pentavalent in the silicon atom crystal, so all the semiconductors are usually like this, only silicon, germanium having 4 electrons. So they are having 4 electrons. Can you notice this is one more extra electron, which is not bounded by anything, because all the 4 silicon crystals will be combining its all electrons, but this one electron will be left. So this is weakly bounded, rest are bonded. They are having good covalent bond. So because this is extra electron present, you can say number of electrons are greater than number of holes. In intrinsic semiconductors, you had number of electrons and number of holes equal. But here what is happening? Number of holes are higher, because now this is just one segment of the crystal atom. No, like the entire crystal atom will be having more number of phosphorus, and more number of phosphorus will be giving rise to more electrons, right? So weakly bounded electrons, these are having energy 0.045 electron volt, and if the thermal energy, this can make it free electron, this weakly bounded electron. But in return, finally, it will be number of electrons will be more than number of. And C class, since these are donating electrons, phosphorus atom is donating electron, and it's a dopant, because it's not a part of the same crystal atom, it's a pentavalent dopant. So we call pentavalent dopants as donor atoms. We call it as donor atoms. Now see, impurities are always added in very less amount, like parts per million, very, very less amount, ppm. So electrons are generated by 2 mechanisms. One is directly when the electron leaves, means hole creates, right? And one is thermally generated hole, means thermal energy is produced and it is making the electron leave. The above mechanism, same mechanism for intrinsic. Same intrinsic mechanism is happening here also. One additional mechanism here is happening. That is through the donor atom. This is the additional mechanism that is happening. Right, and number density of electrons is much greater than number density of holes, as I have written above also. And class, if you draw the band gap, no, you will notice that no need to write this part. This will become confusing. See, when you will write this, no, see, you will notice that this is ionization energy. This is lying near, very much near. It is lying near the conduction band. This value also you have to remember for germanium and silicon. Class, everything related to germanium and silicon, just remember. Any other semiconductor, do not remember it. That is not a part, but silicon and germanium, at least please remember this. So these are energy level donor atoms. So these will lie near this. So these are ionization energy. You can see this is energy of conduction band, energy of valence band. Now, what about p-type semiconductors? Just opposite to it. Trivalent impurities, like if aluminium has been added, can you notice 3 atoms of the aluminium, let's say one here, one here, one here, all the 3 atoms of it, the not the 3 atoms, sorry, 3 electrons rather. So the 3 electrons of it, they get bonded, but one atom of silicon which will be left, it means you are having deficiency of electrons. So what will happen? This is not whole. Deficiency of electrons is not whole. Here there is presence of nothing. So we will not say this is whole. When electrons move, that makes a hole. This is not a hole. Here you do not have hole. What will happen? Adjoining silicon atom like this adjoining silicon atom here. Look here, this adjoining silicon atom will get removed and it will contribute to hole formation in the last part that is left. Now aluminium will be able to complete its octet along with silicon. Now this electron that has moved, this creates a hole. That's why we say number of holes are greater than number of electrons. Please class understand the difference, why we are not considering the lack of aluminium's octet as whole. Right, it is the lack of, there is no electron. You can say no electron is whole. When electrons move, the vacancy that is created, that deficiency is known as hole. So this electron skips up and the hole is now available for conduction. So each atom of aluminium contributes for holes. So that's why we have number of holes more than electrons. And since this aluminium is accepting electrons from the other silicon bond, we call the trivalent atoms as acceptor atoms, and these are also added in parts per million. Right? So same by 2 mechanism, one are auto-generated by the atom only, acceptor atom gives one. Another are thermally generated. Thermally is exactly similar to intrinsic mechanism. This is the additional mechanism that we have. And here, this lies in near the valence band. The energy band, no, this lies near the valence band. So now this is just a summary. I'll repeat it myself. C class. In N type of semiconductors, when there are N type of semiconductors. Look here carefully. Electrons are the majority charge carriers, while the holes are the minority charge carriers. Because this is very important for your next topic, that is PN junction. Please class, very small topics are left now. Do not leave all these topics. These are important. So because number of electrons was greater than number of holes, so the majority are electrons and minority are holes. And for p-type semiconductors, majority charge carriers are holes and minority charge carriers are electrons. If you remember this, the upcoming topics will be very clear for you. Right. And class, see, number or density of electrons is Ne, number density of holes is H. But in intrinsic semiconductors, number of electrons balances number of holes. So how will we write this? So for that, we write it as Ni only, number density of intrinsic semiconductors. And this is one relation, Ne into Nh is equal to Ni whole square. That gives a relation between, you can write just one, no need to write both these. This is a relation that gives, this is actually a formula that gives a relation between Ne, Nh and Ni. Note it down. Any doubts you have in between, ask me. It is very easy. Just write down, note down this, but still if you're not able to understand anything, ask me, I'll clarify it. So it is a major topic that has been completed. One topic was this only. 2 major topics are there. Now second major topic is PN junction. That we'll see. First note it down. did you all write this part? I think I just put it till N type. Yes or no? This
No,
part?
ma'am.
Okay, write down this as well. Because this is a basic difference. Just text me done. Samira, you do. Then I'll scroll it. I didn't remember that this was part also. Just now I recollected it. C class regarding PN junction. See, PN junction is what? This side is doped with pentavalent impurities, and this side, one side is doped with trivalent impurities. So one will develop as P type and the other half will develop as N type. It is not that two crystals have been joined with the help of some ligazing material. Both the one single crystal, when one half is doped with P type and one half is doped with N type, that is known as PN junction. This junction that is developed is known as PN junction. Now see, two processes are acting, known as diffusion and drift. So what is PN junction? It is a crystal doped with pentavalent impurity in half portion with trivalent impurity in another half portion, so that half of it acts as P type and the other half acts as an N type. Junction means boundary between P and N. So simple, single crystal doped with P type, doped with pentavalent and doped with trivalent, making it P type and N type. Now in P type, what did I write you? What did I make you write just now? That holes are majority charge carriers. So you can see there are so many holes present, while very fewer electrons are there. While in N types, large amount of electrons are present because they are in majority type, while holes are very few. Just to understand this, you will understand what is this diagram that I've written. Now, what will happen because of this concentration gradient? Why concentration gradient? Because on one side you have higher number of holes, on other side you will have higher number of electrons. So what will happen? The holes will move towards the N type, means majority charge carriers of P type are moving opposite, and electrons from N type will move towards P type, meaning that majority charge carriers of N type will move towards P type. So this movement of majority charge carriers, that is holes from P type and electrons from N type, this is known as, this flow across the junction, this is known as diffusion, the first process. Fine. Now see, when the electrons will move from its place near the junction they are exchanging. So when the electrons will move, it will leave a hole, and when a positive hole will leave, it will remove a negative ion. So on the junction, positive and negative layers will be deposited like this. This region is known as depletion region or depletion layer. Fine, depletion region or depletion layer. So P type and N type are two types of materials that are doped in a single crystal, and one type is having majority charge carriers and majority charge carriers are moving. Now you can notice this is an opposite. Here negative ions are more, here positive ion. So this sets up an opposite direction potential also, or electric field also. So because of this electric field or because of this potential, a hypothetical barrier or potential is created. Right, because see, here negative and positive charges are there. So that will allow electric field to produce. You have studied electrostatics. You know how is electric field produced. So obviously because of this region, electric field will be produced. And so a potential will also be there. And that potential, this is not actually a potential battery that has been added. This is just hypothetical. I've added so that you remember that yes, potential is also there. So because of this potential, it will pull positive ions from N type and negative electrons from opposite side, so that it actually counterbalances the process. So what will happen? Electrons from P type will move and holes from N type will move. So this is minority charge carriers moving. Electron is in minority, no, in P type, and hole are in minority in N type. So minority charge carriers are moving. That process is known as drift. This is basically what is happening. And see, when the electrons are moving in diffusion process, so that will create current. We call it as diffusion current. So I'll read out, I think, yes, here I must have written it. C class, in N type you have majority electrons and minority holes, and in P type you have majority holes and minority electrons. In diffusion is the flow of majority charge carriers across the junction. Flow of holes from P to N and electrons from N to P. While barrier potential is accumulation of charges in P and N regions sets up a potential difference known as barrier potential. This difference sets up an electric field across the junction and it opposes the movement of majority charge carriers. And class, as soon as it will oppose the majority charge carriers movement, drift will be developed, which is electric field. Due to electric field, the minority charge carriers move across the junction. Clear? This is a basic phenomena. This is known as PN junction. Here also, this is a PN junction diode. Okay, I'll tell you later. Just note it down, then I'll tell you PN junction diode. Diodes are there in your syllabus. Just PN junction diode, not any other diode. Zener diode, photodiodes, no other diodes are present. Class,
Ma'am, can you scroll up?
yes. Still writing?
Yes, ma'am.
Okay.
Done, ma'am.
Okay. Now see, junction diode, no, is the same thing. It's just that metallic contacts are connected for industrial purposes to make them in contact and of more usage to us. But drawing this PN junction entire time, can you tell, is it possible? Obviously not in the circuits, you'll be drawing this in your exam. So a better representation is that represent P side with the help of triangle and N side with the help of a straight line, standing line. So PN junction can be represented like this. And if N is ahead, so NP junction, same PN junction, both can be represented like this. Now you can put this in your circuit at least. Now two types of biasing are there depending on which side will be connected to which terminal of battery. See here, forward biasing is when the P junction of the battery of the diode is connected to positive terminal and N type is connected to negative terminal. This is known as forward biasing. Forward biasing is what? Positive, that not positive, sorry. P junction is connected to positive terminal of battery, N junction is connected to negative terminal of battery. Right? So now see, for four things you have to remember common for both of these, means just opposite. See, flow of majority charge carriers across the junction will occur. Always remember it's the majority charge carriers will flow because positive will pull the negative electrons and the negative will pull the positive holes. And here the barrier potential's value decreases, width of this depletion region also decreases, and resistance of the depletion region decreases. So just remember these 4 points that will help in your calculations as well, that will help in identification as well. And this is not difficult to remember. 4 points. Majority charge carriers move across the junction, barrier potential decreases, width of depletion region decreases, and resistance of depletion region decreases. Right? This is known as forward biasing. Now, some things opposite to this will happen in reverse biasing. See here, P junction is connected to negative terminal of battery. N junction is connected to positive terminal of the battery. Fine. So what type of charges will flow? Minority charge carriers will flow. Just opposite those 4 points, no, that I'm telling you. So first point, minority charge carriers move, barrier potential increases, and width of depletion increases. Fourth point, resistance increases. Fine. Now see, what are these microampere and milliampere that I've written? See, if resistance decreases, then current will increase. So we have current measurement in milliamperes, but here resistance increases, so current will decrease. So we have very less amount of current. That's why we apply microammeter. This is just the difference. This is showing how width region increases. Like this, electrons and holes keep on adding on side by side. Fine, because minority are moving, so they'll leave up the charges, and this is how it is constructed. Note it down, then I'll tell you how to identify forward and reverse in a series in a circuit. Because rest of the portion is from your current electricity, whatever you have studied in current electricity, rest is exactly from it. Just identification is new and unique that you should be able to remember. Okay, then we'll complete the rest of the portion in the next class now. Okay.